So, welcome back. We hope you have enjoyed this break week and recharged your energies and batteries. We are beginning our week number 7, so congratulations to everyone. You have reached more than the middle of the program. And today we have again with us our amazing and charismatic teacher, Scott, who's going to walk us through the wonderful world of logistic regression. So, welcome once again, Scott. It's great to have you here with us again. The spotlight is all yours.
Fantastic. Sorry about disappearing there for a second. I had to get a pen. It's very important to write things down. All right. Yes, fantastic. Okay, so tonight we are taking a little bit longer of a case. Please note that we've reserved a little bit of extra time for this case. We're doing a case about logistic regression. Wait, top teaching. Oh, yes. Well, yeah, no. They wanted to make sure this is a hard case, friends. So we gotta keep our focus on tonight. Hello, Juan. How are you? Hello, Santiago. Excellent. Yes. Hello, Juan. Fantastic. Yes. All right. So I'm going to take a second to get some. My body is ready. Okay, Daniel. Okay, let's go. That sounds very exciting. Monica, do we have the recording started?
Yes, we are recording.
Okay, fantastic. And we have our live transcript on. So let's get our stuff ready to go. And let's turn on our regressions. Oh, it won't be so bad. EC3. All right, yes, this is the vibe I want. What do you do to psych yourselves up when you're wound up, when you're a little bit scared? This is a tricky one. We gotta put on our best thinking caps for this case tonight, friends. My fellow DS Fray fellows, my fellow fellows. Oh, let's hope so. It'll either be laughs or tears, Jan. All right. So I want to make sure everybody have the case. Is everybody feeling good? Okay. RT is ready. I'm also a little bit. I'm actually in DC right now. I'm actually at the place where I work full time at Interos doing data science work, and so I'm in a hotel room right now, getting this case prepped. But I'm very excited. I told the coffee. Perfect. Data science versus capitalism. Stupid. You guys don't miss a beat, do you? You're just ready to go. I love it. All right, let me look at the threads. Anything else in here I need to see before we really get going? Oh, yeah. Well, you know, how do you say laissez de bon temps rouler in oh, that actually should be a Z, not an X. French is a word. French is a terrible language. So many vowels. So many words. There's so many letters you don't even say. There's so many letters you don't even say. All right. Yes, coffee. Okay. We need to get focused. Let good time roll. Perfect. Okay. So today, I want to set up some framework for how we're going to be thinking about this case. So the big thing is I want to focus on here. We're focusing tonight on one of the most important types of analysis tools we will use. This tool is called logistic regression. This tool is called logistic regression. We call it logistic regression. Well, we'll get into it, but it's a little bit different than anything you've worked with before. We want to start at this project from a place of strength. And so what we're going to do is say, okay, what do we know about ordinary least squares regression? Everybody remember ordinary least squares regression, OLS regression? We're going to take all the things we learned from that, and we're going to try to apply them to a new context. My search bar. Oh, yeah, well, you know, the lovely OSL, yes. Ordinary least squares is so beautiful. Well, we're going to take the intuition. We're going to take the intuition from ordinary least squares regression. We're going to put items on a page, and we're going to try to draw a line through them, which is a very important process. We have to draw squiggles. It is very important as data scientists that we draw very, very good squiggles. This is our most important task. You must draw good squiggles as a data scientist. So I'm actually also going to try to do some drawing tonight. We'll see how it goes. The other thing I want to focus on tonight, the other big thing I want you to think about and remember is that regression is a powerful tool. It's a very powerful tool. It's one of the best things in your kit. But before you do regression, yes, exactly, data scientist job requirement, squiggle drawing. Before you focus on your regression, the thing I want you to remember is that at its core, all we're doing with what we are doing with regression is taking the exploratory data analysis we've done and making it more rigorous. We're exploring our data, we're getting a deep understanding of what's happening in it, and we're using logistic regression to help us formulate and systematize, to make a stronger framework for the original idea that we've come up with. So before we do anything else, it doesn't matter how good you are at logistic regression if you don't know how, if you don't have a strong understanding of the data that's underlying it. So a lot of tonight's case is going to be dealing with a very tricky data set. So we have to be trickier than our tricky data set. And we are going to learn, we have to learn to be very tricky tonight. What's the Spanish word for tricky? Oh, ¿cómo se dice tricky? Engañoso, truculento, mañoso. Oh, why are there so many words in Spanish for tricky? I don't know how I feel about that. Complicado. No. We don't. We want something very simple. We want to keep it as simple as possible. Einstein said, make it as simple as possible. And I usually listen to what Einstein says. Aleta, viejoso. We can agree. Why? I still don't understand why they're okay. We need a poll on this. What's the best word? What's the best translation for tricky? Mañoso. I like mañoso. I also like the piñón. So mañoso. You have infinite words. Okay. Very impressive. Lots and lots of words. Truculent. Okay. We're going to go with mañoso. Does tricky mean like clever? Like we want the tricky word, tricky and clever. What's a good word for tricky and clever? Marelo. It's a very, okay, thank you, Abraham. It's a very long case, so we have to get started. Okay, mañoso. I love mañoso. Let's go with mañoso. We have to be mañoso. We have to be a little mañoso tonight because we have a tricky case. All right. So let's start by talking about the business context because the most important thing we need to do. Okay. Oh my God, I'm gonna die. Yeah, I practiced saying "como se dice" a lot to get ready for this case. Como se dice, so I can ask questions. The TAs listened to me try. It was bad. Okay, so we're going to talk about something called online peer-to-peer lending, P2P lending. In the UK, they have an organization called the Lending Club, which is the data we're looking at. Spanish is a very colorful language. We also, I'm sure there is a Colombian and Latin American version of this kind of thing. Oh, sure, let me zoom in a bit. Zoom, 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 zoom. Oh, you know what, we'll do it here. You know, it would help if I knew how to use my computer. All right, is that a little better? Okay, perfect. I like my little GUI. I don't like, there are too many hotkeys to remember. It's a lot for me. Like I try to keep the important stuff in my brain. Hotkeys are not important. Logistic regression is important. This class is powered by data scientists drawing squiggles and trying to make them make sense. All right, online peer-to-peer lending. Online peer-to-peer lending. Instead of lending money to and from a bank, individuals are lending money to and from each other. Really cool idea. Has changed a lot of things about personal finance and small business loans. Really great opportunity for lots of people to help each other out, and build on cool things. So what are the things we need to know here? A big core part of what's going on for every P2P lending company, they have to reject borrowers that have a high chance of not paying off their debts. They have to reject borrowers with a high chance of paying off their debts. Yeah, Matteo, it's like crowdsourcing, but for small business, for small loans and from person to person. So instead of just giving people money from crowdsourcing, you offer loans. There's lots of different organizations that do that. Are there any in Colombia that do this? The one I'm most familiar with is Kiva. Yeah, okay. Jose, do you know the name of any of them? Cooperatives, yes. Juan Pablo, exactly. Oh, go to. Sure. Someone always brings up the shark loans. Okay, that looks good. Yeah, okay. So I think we're getting the idea. It's loans from people to people that don't have a bank. Oh, interesting. That's interesting, Vivian. I did not know that. Okay. I think you all are getting it. DMG survive. Okay. So one thing that we're trying to do is understand this idea about what a verified source of income is. Let's go look at the core business problem here. We want to make our companies work as efficient as possible. Oh, that's scary, Edna. That's very scary. We want to make our process as efficient as possible. That's really important here. But we want to check out and see whether this verification process that we are using actually adds value. So one thing we're going to talk about here is verifying the income source of an online loan applicant before approving their loan. So on the surface, that idea makes sense. What the company is asking us to do is say, hey, it's really annoying and time consuming to confirm how much money someone makes by getting a pay stub, by getting an employment letter, by getting other kinds of bank records. We don't want to do that. We want to see if we can drop that step from our process because it's difficult and time consuming. Can we use other information to get the information we want? All right. So let's look at the other information here. We have data from the Lending Club, which is a P2P loan organization that operates out of the UK. Notice also our data comes from 2007 to 2012. That's not going to matter a lot for our context here, but you should always check data and where data is coming from, especially financial data. And because there are big financial events that happen that impact the kind of things you can see in this data, that you can see in data. All right. We also are getting very lucky because we're getting information about whether a loan was fully paid or charged off. So charged off means written off or written down. Basically, this is a loan where the payer, where the person was not able to repay the loan financially and the loan had to be sent to a collection agency or otherwise discharged and the company lost money on it. Are we clear about what charged off means? Yes, no? Okay, perfect. All right, we have about 50 variables, 50 different variables. That's a lot of variables. I don't know why we have so many. It seems ridiculous. That describe the borrowers and the loans. But for the sake of our process tonight, we will focus on a preform screening of just a handful of relevant variables. Excuse me. So we're going to look at annual income. We're going to look at the Lending Club credit grade, which is a rating that the Lending Club makes about how risky they think the loan is. And we're going to look at whether or not people own their own homes. So why do we think all of these? Why would things like annual income, the riskiness of the loan type, and home ownership, why would these be relevant to whether a loan gets fully paid or charged off? What do you think? Calculate the risk. Okay. Economic stability. Good. Yes. To know if they are risk people. All right. Yeah. Good. Perfect. They're in. Yes. David, that's perfect. They're indicators of financial prosperity. Like it. Yeah, Viviana, Ernesto, perfect. Yes, these are also ideas about collateral. Home ownership is collateral. Perfect. Yes. Nicholas, are you good to go? Are you going to go find them if they don't pay? I like it. I have a related question for you. Will annual income and lending credit grade and home ownership be correlated? Will they be statistically correlated or related to each other? What do you think? Possibly. Yes, most likely. Okay, perfect. All right, not always, it depends. Okay, yes. But it is reasonable to think, it is reasonable to assume that there may be relationships between these things. These are not perfectly independent things. Perfect. Yes. Okay, perfect. Good, Sebastian. Yeah, that sounds about right. Banks will only give you money if you already have money. That sounds like a very clever idiom. Okay, yeah, well, there you go. Okay. So the last thing we want to focus on tonight is that we're using logistic regression to answer our question at hand. And then we're going to talk about why we need to use logistic regression. But one of the big reasons is the kind of data we have. When we have this fully paid or charged off situation, we have a very unique kind of data. We have binary data. And so we only have two outcomes. The loan is either paid or it's charged off. So that means we will need to use a different set of techniques, and we will have to be a little tricky about how we build our regression this time. All right, so we have 4 things we need to do here. We've got to explore our data to get a rough idea about how each variable in the data set interacts with loan status, because again, we need to have an intuitive understanding of what the data does. No one is going to listen to you as a data scientist if you say, look at my model, it's very pretty. It is very good at drawing squiggles. And then people ask you, what does the squiggle mean? And you say, meh, I do not know. That's not a good data scientist. That's not who you're going to be. You need to be able to develop and talk about what your squiggles mean. Yes, this is very, this is very important. You must be able to explain your squiggles. I don't know the difference between those. You're importing 2 different classes. Or excuse me, you're importing 2 different methods. Andres, don't worry about that a whole lot yet. It'll become clear as we move through the data. I think those 2 things do slightly different things with the packages that are available. Okay. So we've got our packages here. We can look through these and see what we're going to be working with. It should be pretty clear. We're using our classic tools. We've got our Seaborn, we've got our stats models, and as Andres has pointed out, we're pulling in 2 slightly different versions of the stat models tool. These 2 these 2 methods have slightly different effects and slightly different things they do, and I believe we'll need both of them to do this case. Every time I see import numpy as in D, I see a person of culture. Yes, absolutely. Very, very fancy. Gotta love people who import numpy as in P. All right. And notice I'm importing OLS. We won't actually need OLS to do this case. Ordinary least squares. We don't need it, but I'm pulling it in because I want to show you why we can't use OLS regression. The spicy libraries. I have no idea how to spell that. Okay. So before we begin, let's look at the data that we have. I'll bet. Yes, kind of. So there's several different kinds of logistic regressions. There are and there are three broad categories you can look at. You can look at logistic regression or binomial logistic regression. Binomial means two. There's multinomial logistic regression, which can handle multiple different classes and types. Yes, it's a whole, well, it's actually pretty functional. The chat, what? No, what? No, why? Brian, that's terrible. Don't even go there. And we can also use, there's also a kind of logistic regression called ordinal regression, where we can organize something in order. Was I ringing? Did you guys hear that? That was very scary. Is somebody trying to call me? I have no idea what that's about. We'll continue on. It is. Can ever, like, am I going crazy? Am I just hearing the sound of like a ringing in my head? Okay, good. I'm just going crazy. Awesome. Fantastic. Yes. Scotty the data scientist is going crazy. I am in the upside down. All right. So we're pulling in data. We've got our PD read CSV. Fantastic. And we're looking at our loan status types. None of you are helpful right now. This is not helpful for us. Not making me feel good here. So we've got our loan status. Now, what am I doing here with this little line of code? PD API types, categorical D type. What am I doing here? What does this line of code do? What do you think? Mateo, that is correct. We are making the values a categorical variable. Yes, we are setting the fields as categories. Perfect. David, we are setting them as that. Yes, Santiago, that actually would work. We could convert bools to categories as well. Yes, we're converting these into categories. We do this because it's a good data practice. We know that these are the categories that we want. It also makes it easier for us to do some of our analyses later. We're also doing this for our verification status and our verification types. We're also setting this up for our employee length types. Now, this one is a little bit more of a, I don't want to say subjective, but we could treat these as integers, or we could also treat these as categories. In the logic of what we're trying to do, I think doing it as categories is better, but other people would have different opinions. It sort of depends on what you think about the distance from what the difference between 1 year of a job means in terms of creditworthiness and in terms of riskiness. One big thing I want to go over are these three types. So we have three different types of loans here. We have loans that are not verified. If a loan is not verified, or if an income source is not verified, that means we don't have any idea about whether or not this is actually true information or not. We haven't done any external checking for these loans. The second type of verification we have is source verification. Now, source verification sounds a little bit strange. Source verification, yes, just two options for the loan status. Source verification means that we don't know how much money the person is making, but we do know that we have some record that shows that they are currently employed at a certain employer. So usually that means that someone has sent a letter or sent a marked out pay stub that says, yes, I currently work at Apple, and you can see that I work at Apple based on my little document. So source verified means we don't know how much they make, but we do know they work at a place. And yes, Daniel, very good. It is a lot like being partially verified. Very, very similar. And if a source is verified, we have information about the actual amount of money that person makes for their annual income. So these are in rough order. They're not in a, we're treating them as categories, and we can definitely say that they're in an order. Ha, Andres, that is an excellent question. So there's not much we can do about that. Sometimes data gets misplaced, and we can do some checks on that. But that's a part of what we're going to be doing tonight, actually, is checking to see if there are inconsistencies or unusual realities or unusual information that that might show us that a categorical variable is incorrect or is not right. Unique is a great way to look at the number of unique elements. That's perfect. But we're doing something other than that. We're also converting these into categories, which will help us later on down the road when we're doing our statistical analysis. Yes, DF home ownership unique will tell us what the unique values are for home ownership. Alexander, that is an excellent question. It is tied into a bigger question about what you think the measurement means. So we're thinking about the length of time a person has been employed at a particular place. And what we're saying here, notice how there's kind of a nonlinear relationship, right? We say we have a category that's 1 year, then we have 1 year each for these, and then we have more than 10 years. And so what that's telling you is that we have some of our pieces of information here have a linear relationship, right? The difference between 1 year and 2 years is the same, but we don't have that same linear relationship for things that are less than 1 year. And we also have a drop off up here at 10 years. So what this is really, this is partially a judgment call. You could treat these as integers. I think it's a better idea to treat these as categories because we don't necessarily expect there to be a perfect linear relationship between that's not a bad, wait, what's that? Yeah, that's actually a pretty good question. This is the way that this code is written. I think the reason why we do it this way is because we're trying to pull in these specific D types, which helps us make better descriptions of these. But you could also do it that way. Okay. Ba, 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 ba. So the big difference between this code and that code is that these allow us to explicitly define what the category labels should be. And if you just use the as type category, you can't actually specify what those specific things should be. So it'll treat everything as a category. This helps us deal with errors like small kinds of errors. Like if somebody typed in 5+ years for something that they put in, this would block out and throw that data out and would classify it outside of that. So it wouldn't screw up our analyses and wouldn't treat it as a unique category. So the reason why we're doing this more explicit categorization is because this allows us to specifically identify what the values for the category should be. The code that Franklin posted, the as type category, does not allow us to specifically say, here's what this category should be. And in terms of what we're doing right here, we want to be relatively specific about what we're doing because we know what these values should be. Sometimes you get data and you're not entirely sure what the categories should be because the data dictionary is bad or because you're working with the data set you don't know very well. We have a lot of information about these. Do these categories come from the unique? Yes, Ricardo. So we have good information from the P2P folks about what the values should be for each of these. So we can explicitly identify what the category labels should be. And that's why we're writing this more complicated D-type code. Yep. Categorization is also useful to avoid outliers and also means we don't have weird little things. I don't believe we're explicitly identifying an order here, but I could be wrong. Okay, so I want to keep moving for the sake of time. We're putting in rent, mortgage, own, and other for our categories of home ownership. And we have two specific categories here for, and excuse me. So I will also say that I think in your code book, these are not split out this way. I specifically moved these over so that these would be a little more readable. I like it when I can see a list in vertical, but some people just put everything in. Make the categories as numbers or as words. Which, Ivan, which variables are you talking about? So the short answer is that not a lot happens, but you can get weird results sometimes, or results that are unexpected if you don't set these up as categories. By telling the pandas data frame that we want to treat these as categories, it will be able to create visualizations that are a little bit crisper and cleaner and tell us more information. It will also make doing some of the analyses that we want to do, like chi-squared analysis, run a little bit better because it'll be able to process the information more effectively because it knows what we're trying to do there. So it doesn't necessarily matter on a data set that only has 30,000 records in it. But if you had a data set that had 300,000 or 3 million, setting these up as categories can increase your processing time and also can make it more efficient for the computer to run what you're trying to do. It's also a good practice because we know that these are all going to be treated as categorical variables, and that's largely what we're doing with the data. It also is nice because it allows you to do the one, like if you are going to do one hot encoding later, it will allow you to do that as well. With a little more ease. And again, Diego, then the relevant variables we're going through are these ones right now. Verification status, employment length, home ownership, term, grade, and then we'll have a couple of other variables that are integer variables. But we're going through the categorical variables now. Right, so John, that's exactly what we're saying. If it doesn't match, then we don't use that data. Yes, Harold, that's exactly that's part of the value of using these categorical variables. So align with what I don't remember who said it earlier, but when we're doing our categorical variables like this, we won't have little outliers from things that don't fit in the categories that might screw up our statistical analysis. So this is another good reason to use these categorical variables as a nice, useful way to help make sure our visualizations look good, make sure our statistics are clear, and remove and reduce the current concerns we have about somebody putting in incorrect data or invalid data. Why are we So Andres, I think your question is why are we using these specific categories? Is that right? So part of the reason, so this is categorization, Sebastian, categorization will help the classification model. It will give it more points. It will give it more information about what it's expecting to see. So it will make better, it will evaluate our model will work better. And Andres, the main reason that we are setting this up in exactly this way is because this is the information that the blending folks have sent to us about what is in their data. In this particular case, I'm sort of reading you the data dictionary, which is down here. I don't know what that is, Yoni. but we're setting these, but Andres, to answer your question, we're setting this up with exactly these things because this is the information we have from our clients. Yeah, Julio, they should be the same, right? Because we only should have those two pieces of data in there. They would be different, and it would matter if they were different if somebody had made spelling errors for charged off and it said that and some of the data was labeled as charged off, or if somebody had said fully paid or put other pieces in there. You can't use category. You that's well, actually, you can do that. You can use a parameter called include equals all, but you don't need to do that. Remember that the describe function only works on float and integer variables. It doesn't work on categorical variables, and it never did. So that's okay. That's expected behavior, Johan. Yes, Manuel, you can use describe include equals all as a way to look at the categorical data as well. It's a little bit confusing when you do that because of how it interprets information about the mean, but it can be helpful. Yes, Luis, you're getting the exact idea. In this particular case, we have very clean, nice data, so our categories are already set. In general, it's a good idea to explicitly specify categories so that if you have data that has errors in it, it won't impact your analyses. So your data won't rely on people type spelling errors or others. Your data won't be altered by people making spelling errors or by people misclassifying data. Doing this as a practice helps you encourage best results. Why the space in DF term values? Luis, what are you looking at? Yeah, no, you're asking you're asking the right questions. Oh, yeah, don't use that. That's just me being dumb. That was me going on a spacing frenzy. Don't use the spaces there. Yes, so Abraham, that's exactly right. We're going through this in great detail, and I'm spending a lot of time talking to you about this data because if we don't have this information, then we can't use it. Yes, we don't want to include the rows that have a type error. Thank you, Gabrielle. So Juan, this is not quite a data pipeline. This is data validation. So data validation is an important part of the work you do as a data scientist. And a part of data validation is making sure that you know what values and fields to expect inside of a data set. It's always good to go through this and check and talk through this because data dictionaries are often wrong and they don't have the right information that you need. To give you an example, I work for a company and do financial analysis very, very frequently. I work with a major financial organization, and very frequently their data dictionary is wrong. So they will say, oh yeah, there are only 3 categories of loans in the data we sent you. So they'll say, oh yeah. We have 3 categories for verification status for loans. And I'll be like, okay, cool. What are those 3? They will tell me. And then I'll see like 8 types in their data. And I'm like, ah. So we're really lucky today because we're working with data that's relatively clean. I'm trying to teach you practices. And again, you're all being skeptical, which is what you should be doing. Data scientists should be skeptical. And you're doing a great job of that. So please keep it up. So if data doesn't match those, if an observation doesn't have data that matches that, it gets excluded from further analysis. What? Huh, that's weird. All right, I guess they included a space in that. That is That is surprising. Okay, don't get rid of those spaces. That was not me going crazy. That was supposed to be there. Yeah, here's what we can do. I wanted to spend some time going through this because I think it's important to understand A, why we're doing categorical variables, and B, what's in the data. But I do agree we can move forward. If we can put together a thread like what Juan suggested, I'll be happy to go through those and answer any questions that we have there. All right. So one other thing I want to call out before we go finish. Yes, very good, Franco. Data scientists should be skeptics. How do you say that in Spanish? ¿Cómo se dice skeptic? Espe Espestico? Wait, why are there so many words for tricky and only one word for for skeptical? I like it. I like it. Incredulo. Tricky is a tricky word. Esceptical. Esceptical? Esceptical. Okay, perfect. Esceptical. Yes, okay, perfect. We have to be esceptical. Oh, yeah, no, I mean, Dorian, please feel free to give me, yeah, English is terrible. You all know it's full of words. It's full of stolen words. Like English language is just like, pecadillo. I like that word. It's Spanish. We're just going to use it. Whatever, it's fine. We don't care. We are not very skeptical. Very tricky. Oh, what? That's amazing. Okay, let's keep going. So the other thing I want to point out here is that we are doing a little bit of data cleaning. So let's again walk through a little bit of our Python code. This is a really common thing that people will use. So let's talk about what's going on here. This is a little bit more, this is a little more codey and a little less data sciencey, but important. So I'm defining my data frame here. I'm defining my variable name here, the interest rate. What am I doing to it here? What does the .str method do? Perfect, converts to a string. Ding, ding, ding. Winner, winner, chicken dinner. Okay, our strip. What's our strip gonna do? It's gonna remove, right? It is taking value on the right side. Yes, perfect. Okay, we've got 3 pieces there. Our strip is gonna say, hey, in this string, do you have a % sign on the far right side? If you do, go away. Goodbye. You're gone. Carol, that is very good. I want to say it again. Remember that before you do a model, you will always have to do data cleaning and data exploration. And this step usually takes the most time of a data scientist. That is absolutely correct. And the bigger the data set, the longer it will take to clean. And the longer it will take to do exploration. Oh, yeah, you could actually add yes, Luis, that's a good point. You could absolutely use the strip there and get to where you want to go. So this is called method chaining. This is a very useful skill, but basically we're saying we need to pay attention to the order here, but this is a good refresher on some standard Python string manipulation. So we're taking our strip, we're using the R strip to get rid of that percentile figure, and then we're using as type to convert it back into a float, or to convert it into a float, I should say. Yes, perfect, Ronnie. Well, yes, we're converting to float from string. Very good, perfect job. All right. So we've done our work here. So we've converted our data, we've converted the variables we want to examine into categories to make them more flexible and more useful for our analysis, and to reduce the pain that we might experience from mislabeled categories. and we've converted interest rate, which was in a string form we could not use, or object form we could not use, and converted in and changed it into a float that we could use. So, Andres, yes, but it doesn't, for most of the analysis that we are doing, it doesn't matter as much. Like if we treat if we treat 1% as 1, or we treat 1% as 0.01, it's not going to make a big difference in the analyses we're doing right now. We just have to keep track of what that's going to be. So it's a good thing to remember. And it's always good to ask people about that and be consistent about that. But it's one of those things we have to pay attention to. So you'll notice in the head here that we are leaving them as 100s. So we could divide this. So this means that the interest rate was 10.65%. That's a very high interest rate. We could divide this by 100 to get to 0.1065, but for now we're going to leave it. And again, if you want to treat it that way and you want to divide it by 100, more power to you. It won't make a big difference for most of the analysis we are doing because it's a simple linear transformation. We're not changing the order. We're not changing the relative order. Mike, I am very glad that you have identified the most important thing about this data set, which is that it is full of people who like to party much harder than we do. A gota gota? Oh, wow. What's a gota gota? Is that a shark? Yeah, these are really high interest rates. These are also loan shark. Well, it's good. You're teaching me really important Spanish words like gota gota. And all the words for being tricky. This is very good. Maybe I should just start my own little, little loan shark plan after this. Gota, it's gota a gota. Okay, gotcha. Drop to drop. Oh, that's, oh my, that's dark. Okay. All right. So we have these pieces of information. We've got our things set up, or we've got our categories set up here. We can see some things about this. I also want to call out this bit over here, the grade. The grade is an estimate from the lending club about the quality of the loan, and it's related to the loan amount, the interest rate, and the term of the loan. This doesn't perfectly match, but full of dangerous words tonight. We are full of all kinds of dangerous words and ideas. Oh, okay, Columbianism. I like it. All right. We are really excited about this gato a gato business tonight. Yeah, so these are interest rates that are like a credit card. These are very similar to credit cards. They're short-term loans. They're designed to be a lot like a credit card. All right. So we have 38,000 records. Each record corresponds to an approved loan. I hope these are very obvious to you from this analysis. But that is also something you should check and look at how many, and make sure that the observations are unique. All right. So we have another few little pieces of information down here that give a little bit more information about what's available in the loan. Again, the real thing we're trying to focus on is this first one here, which is the verification status and how it relates to a default. This is the most important piece of information in our analysis. All right. So the first thing, it is an annualized interest rate. Yes, Joni, I believe it's an annual interest rate. I can see we are very excited to talk about loan sharks tonight, which, that's fair. It's a wild thing. But let's continue to focus and talk about the data science. I found out that someone in our group tonight Are you posting, Julio? Yeah, okay. Thank you for posting those very helpful Wikipedia links, Julio. So what I want to do right now, we have our data set is a binary data set. The outcome we're looking at is, was the loan charged off or was the loan paid off? Okay, Julio, we get it. Yes, thank you very much. Okay. So I want to look at these box plots. And I think we can, I don't want to go over the specific things here. We're using Seaborn here to pull this data in. The only thing I want to call out here is when I'm setting the Y scale to log for the income data. Why do you think I might be doing that? It's not quite normalizing, but you're on the right point. Andres, yes, perfect. Yes, Andres, the data is too large. We're just shrinking the range a little bit so that it's a little more interpretable. Yes, it's to make it a little bit less heinous to calculate. I mean, we can do it without that, but we're not going to like it. If I cut that little piece out, it smushes everything. Is this guy right over here? Is that very legible? That does not look legible to me. Yeah. So we add that little bit in here. To help us better visualize that that poor box. It's a poor little box plot. You smush it all together. You pulled it apart. And you like, the loan sharks got to that box plot. That's all I can say. Okay. Extended case. No, yeah, just take the log of everything. Just take the log of everything. Drop by. Okay, Sebastian. All right, so I got a little challenge for y'all. I'm going to give you, what do you think, Oscar? 2 minutes? Take 2 minutes, look at these box plots and tell me what you think about the relationship between loan status and annual income, loan status and interest rate, and loan status and loan amount. So I'm going to be quiet for 2 minutes. Oscar, if you can drop something in the polls and answers bit. Let's give you all 2 minutes to think about what that's going to be and post your answers and post your responses to the question in polls and answers. What do you observe from the box plots above?
Can you give me a second, Scott?
Absolutely, no problem. Think about how a box plot works. Think about the information that's in a box plot. So Ricardo, folks, colleagues, please remember to post your responses in polls and answers. If you have a specific question you want to ask, do drop it in the live chat and I will try to explain. Please answer on the thread. Please answer on the thread. I will keep singing until you answer on the thread. Get all these wonderful answers on the thread. I really like the idea of adding some group scatter plots. That is a totally reasonable one. That's using a grouped scatter plot or a group scatter plot would be a great way to look at this as well. It would be a little bit, the only reason I wouldn't necessarily want to use the group scatter plot, well, no, you could do that. If you wanted to investigate the relationship of two of the variables and then use the charged and loaned, charged off and the loaned as a color scheme in a group plot, that could tell you a lot of information. I would probably not use a predictive power score. I don't, but that's just me. I don't like predictive power scores. I think they are computationally expensive and don't give you any more information than a correlation does, but not everyone feels that way. So I imagine that you've had some folks who have talked about predictive power scores and like them. I think that they are, I would rather use a correlation and a scatter plot to tell me that information, but that's my personal preference. But actually, Juan, I do really like the idea of using group scatter plots, especially if I wanted to get at the relationship between multiple variables. So if I wanted to look at annual income and interest rate and the loan status, I could use a group scatter plot to do that. Okay, it looks like we're dried up in polls and answers. Let's see what we've got over there. All right. Let's go grab a random question here. Okay, Gabrielle says only in the logarithmic view there is a difference between two variables. That's true. Okay, Alexander says the interest rate looks like a good candidate to reject a loan. That makes a lot of sense, right? Because we can see the big difference in the means. All right. And Franklin says annual income and loan amount do not seem to be good predictors of loan status. On the other hand, people with higher interest rates seem to charge off more than those with lower interest rates. Good. So when we're thinking about analyzing a box plot, you all are hitting on the exact points. We can see a small difference between the medians for the loan status and income rates. So there might be, Mateo, actually, no. Well, and that would work, yes. So the thing about, it's going to be looking at a different analysis, but the analysis that we want is the analysis between the log variables and not the analysis between the raw scores. A log transform is an order preserving transformation. So some statistical analyses will change because of it and some won't. It depends on what kind of statistics you're using. Okay. Yep. Okay. Good job, Romanger. So the short answer is that a log transformation doing the log transformation helps you get the statistical analysis that you need and will give you a more apt answer. Whereas leaving it untransformed will turn the data into a non-normal, will create a non-normal distribution that can skew your analysis. So in general, when we're trying to analyze these, we want to look at those differences. We want to look at a log distribution for income as opposed to a non-log distribution. All right, I feel like I've over-explained that. So again, this information here is really important. The two big things I want you to think about are this line right here. Where is that median? And again, we see a little difference here. We see a big difference here, and we see almost no difference here. The other thing to look at is what are these little guys up here? What does that little bar tell us? Anybody remember? It's not the max. There you go. Yes, the interquartile distance. The 75th percentile. It's telling us about where outliers are. Now, what we can like, I also like to look at the outliers because what we can see here is that it tells us something about where variation is happening. Statistics fundamentally relies on variance, right? There has to be differences, variation in the results. So looking at where your outliers are, looking at looking at where variance and standard deviation is high can tell us a lot of information about what's going to happen and drive our statistical analyses. And what you can see here is that there is the 75th percentiles here are really similar. We have more outliers up here and a few more outliers up here and far more outliers on these fully paids. It's the 75th quantile, not the 95th quantile, Nicolas. Julio, perfect, good job. Oh, did we lose Monica? Okay, we are not moving very fast with this. Okay. So we've already kind of talked through this idea about these plots and whether we can conclude that annual income does not play a significant role. I think we can say in general, it doesn't have a huge effect. But we can also look at this a little bit here. So we've done a visual check. So now we're going to add one level of statistical rigor. And we're going to continue to ratchet up our statistical rigor as we go. So somebody asked before, Matteo, I think you asked specifically about what we want to do in terms of analyzing the data. And when we're thinking about analyzing this data, excuse me, we're going to look at you could use df-describe for this. Yes, that will tell you about the mean. That will give you some of that same information that we looked at in the box plots. So one thing I want to point out here, though, is we're trying to look at our t-test. So what am I doing up here? What am I doing in line 1 here? Good. Yes, we're getting the median income. Yes, we're creating a filter. Exactly. Perfect. We're creating a filter here for the charged off, the annual income, and the annual income for the fully paid and the differences there. And we're creating a t-test, or excuse me, a t-test. Very good, Julio. Thank you. Now, remind me, what does a t-test do? What is a t-test going to tell me? Correct. It is a test for whether the means are equal. We get a value that is really, 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 really small. Very good, Rahman. Yes, we're getting a value that's showing that there is a statistically significant difference, which means that there's a statistical difference between the mean score of the loan status for the annual income between these two between the charged off and the fully paid people. Zero. So that's exactly what this is telling us. This p-value is telling us how likely it is if we had another set of similar data of this type, whether we would observe the same result again. Right? We're trying to test whether it can reject the null. And in this case, we can reject the null pretty strongly. So how do I very good, Maria. The two data sets have distinct means from each other. But this is showing that these two things are really, really close together. So what should I do with that? I don't understand. What do you think I should do? Not exponentially. Have we talked about practical significance and statistical significance? Perfect. This is a pretty good example of practical versus statistical significance. We do observe a statistically meaningful difference. We don't observe a big practical difference. We don't observe a big difference in the mean in those two means, or those two medians, excuse me. So there is a difference, but we need to do further analysis to see whether we can do anything with this. Right, it's not a big difference, John. mean, depends on whether you think 6,000 is a lot. But this is a question about what we should do next. So we've done some analysis, we've done some rigor. Should we continue to conclude income in our models or not? Ernesto, I'm in general agreement with you. We should include income in the model. So we can't really use the medians for performing the t-test because we would need to use, because we're looking at the whole distribution. I mean, we technically could, but that wouldn't be like an appropriate way to do that analysis. Yeah, perfect. So we can compare these two things. Okay. So the next thing I want to do here, in addition to my analyses, oh, I don't know what that was. Okay, let's continue going. We're going to create a little function here. What do we all remember about our, this is going to help us answer that go back to that core question about loan verification status. What do we remember about a chi-squared table? This function is going to create a crosstab. So it's going to be able to tell us for each of these subcategories what kind of analysis we're going to see. Perfect, it's a contingency table. Yes, that's exactly right, Marcela. Yeah, it's a kind of adjusted frequency table. Good job, John. All right, so this this is not good. What do you see here? Right, so that's true. They don't have a similar sample size. But I'm really interested in this piece here. Based on what we were thinking about, what was the expected result? As we increase the amount of verification, will we expect the percentage of loans that are fully paid to get higher or get lower? Higher. Higher is expected. What do we observe? It's lower, right? It's getting lower. As we do more work to verify it, we're not getting better at we're not getting better results, we're getting worse results. That doesn't sound right, does it? This is an everything is fine moment. Here in Colombia. Oh, good. Yes, thank you, Laura. Thank you. Everything is fine. My data is really good. Don't worry about it. If I showed this to the vice president of finance for the lending club, he would, or she, or they, excuse me, they would be absolutely shocked. They would be like, what is wrong with you? This is crazy. You're a terrible data scientist. You are not good at drawing squiggles. So this is a counterintuitive result. This kind of thing is the thing that freaks people out when you're trying to present this to stakeholders. So what do we need to do here? We need to go through this data. Yes, he would send you to Agata. Yes, exactly, Mike. He would send me a gota. He would send me a gota. So don't judge my squiggles. Perfect. All right. So we need to do some further investigation. Exactly, Luis. We need to understand why. So we've kind of gone through this bit about what our possible solution is. So we need to do some more analysis here to figure this out. It's like a flamingo. I do not know what that means. That sounds very scary though. Flamingos are very dangerous birds. So notice that when we do, oh, okay, gotcha. It's a company. All right. So we're going to do a Javier. Yes, we're going to look at whether it's a Simpson's paradox. Why is this occurring at these different loan statuses? Are there differences in the characteristics of the loans that are driving these results? The chi-squared test is showing us that this result is true. Like sometimes the results, sometimes if it's a little bit more of an edge case, the results might look like they're going down, but they're not going down by a big enough difference to actually be statistically meaningful, statistically significant. The chi-squared test here is showing us that these categories are statistically different from one another enough that we need to do further analysis. All right. So we've kind of gone through this bit here a little bit, and I apologize. I'm trying to get through a little bit more. I know we also need to take a break in a few minutes. Again, this is a long case and we are a little bit behind schedule. So I apologize. I need to continue to move forward a little bit. All right. So what I want to look at here is, I'm going to speed through this part a little bit. But one thing we want to look at here is to generate a contingency table that includes both the verification status, the loan status, and we want to look at another characteristic. We want to look at the term of the loan and the home ownership. So what we want to see is if we're going to observe the same pattern. Because what if it just happens to be that the home loans have a sort of explanatory effect? Or what if the terms of the loan have an explanatory effect on the results that we see? All right. So we're going to look at this here. Again, we're going to use our crosstab function here. We're going to drop our columns that are missing stuff or have these alls that we don't really need. And we're going to look at our contingency table. So again, we want to pay attention to the pattern here in this column. Perfect, Ernest. Yeah, that's a really good intuition. How will we test that? Good. Mateo, again, we're seeing these results are lower. For rent, in the rent category, as the verification increases, the rate goes down. Yep. So is rent really explaining are differences in home ownership helping to explain what's going on? Nope, not at all. So we can rule out that explanation. All right. What are we seeing here? When we stratify, when we break things out and use the additional contingency in our contingency table, what's happening? We see generally a lower rate on the higher term, but let's look inside of that. So inside this term of 36 months or 3 years, is there a big difference between the non-verified and verified? It's more stable, right? Not as big of a difference. What about in the 60 months? Are we seeing a big difference there? More difference. but it's a lot, the difference is disappearing, isn't it? Right. Overall, there's a big, the fully paid is lower on those 60-month loans, and it's higher paid on that 36-month. So yes, there seems to be a pattern, right? What's happening here is that the difference between these terms is driving a lot of this difference for verification status, right? We can say, once we account for the term of the loan, how long the loan is, that seems to be reducing the impact and those different, that paradox that we are seeing with the verification. Yeah, they just don't pay their loans, Daniel. It's terrible. Those longer term loans are riskier. Okay, so I'm going to show you a table, and I'm going to show you a table here. Ooh, don't want to show you the answers. Oscar, this might be a great time for a poll. Thank you. Yes, polls and answers. Which of the following conclusions are correct? 1, 2, or 3? Oh, select all that apply. Okay, everybody on 2. Good, people are getting 2. I see 39 there. That's really good. That is exactly what I want to be seeing. They did. Okay, are we getting more answers here? Okay. All right, so I think we're getting the idea. We're getting a good sense here of this 2, that 2 is correct. So let's review the answers. Note that all 3 of these are technically correct. So based on that stratified contingency table, the difference in the probability of full payment between income verified and non-income verified users might be attributable to the effect of the loan term, right? And again, that's exactly what we said. When we don't take into account term, we see that paradox emerge. Once we take into account the term, we see those differences shrink. Yeah, I know it's confusing. Yes, Edgar and Jason, that's a fair reaction. So one of the big differences that we see here is that there's probably some kind of relationship between term and verification status. People who have shorter loans may be more likely, more short-term loans may be less likely to get verified. I think I said that right. But the bigger thing here is that once we are taking into account these differences, people are able to see more of that, see more of those, see those answers as we're able to help resolve the paradox. And for part 3, this is again correct by definition, and it may help us to explain why we're seeing this counterintuitive trend. In general, that's right. Users with no verified income have more short-term loans, and that is a part of what is driving this effect. So there's an interrelationship. There's a relationship between these two, between term and verification status, that we did not consider, that is driving that Simpson's paradox. All right. And you can see it right here, right? In the 36 month, we have a lot more people without my verified. And in the 60 months, we have a much larger proportion that are verified. Okay. Oscar, what do you think? Should we take a short break here and then get into the linear regression bit?
Yeah, okay. Let's take a 10-minute break.
Perfect. Let's take a 10-minute break, folks. Please come back at 8:30. All right. So great job on the first part of the case, everyone. I think that song break was delightful. We'll do one more break just so you get a sense of the rest of our evening. That is my skeptical look. So to give you a sense of the rest of the evening, we're going to take another 40 minutes and we're going to talk about our regressions, our logistic regression, and motivate that from our ordinary least squares. Then we'll take a shorter break so we can take a little, what's the word that I'm supposed to use? Helpful. Nope, that's not the word. I didn't write it down. I thought I wrote it down. Apuestas? No. Arepas? Arepas, I think so. Arepas break. And then for the last 40 minutes of our session, we'll talk about the ROC. We'll talk about something called the ROC, which is how we obleas, arepas and obleas. Yes, okay, so we'll take a break. We'll take a break after the logistic regression bit, and we'll have an arepas and obleas break. It looks terrifying. I don't know what to do with that. I have no idea. Is that a space monster? Oh no, that's just Piccolo. Never mind, it's fine. Okay. I'm going to try to go quickly through some of these things. I want to focus on some more of the conceptual ideas and a little bit less of the code. For this next bit, I encourage you to walk through the code and think through it. I want to focus a little bit more in the second half, talking about why our original model doesn't, why we need logistic regression and why we can't use linear regression. Okay. And so this section is a little bit more for the statistic nerds in the house, a little bit less for the engineers, but I'm going to try to set this up so everyone's getting something out of this. Okay, and this is going to be the tricky part. Okay, so first thing we're going to do, here, we're going to pull in our key variables, our loan status, which is whether things are charged or not, our verification status, which is our important variable, our grade, which is how risky the lending club has deemed this loan or the type of loan it is, and the term of the loan, that 30 versus 60 bit. We're going to set up everything with category codes. And again, we can use this simpler version of doing this because we've checked them before during our data validation step. We know that we have the right values and information we want in there. And we're also going to do one thing down here. Now, what is this code exactly doing? Well, I'm taking the value from my variable, I'm subtracting the mean, and I'm dividing by the standard deviation. What that will do is do something to my code called standardizing. We'll standardize it will normalize or standardize the variable. A normalized variable has a mean of 0, and a standard deviation of 1. Yes, it is to make sure that everything is on a uniform scale. Exactly. Daniel, it is exactly like a z-score. Juan, it changes the way that it normalizes the variance. So it doesn't really remove, it's not quite correct to say that it removes variance. It does change a little bit how it looks, but it doesn't take away any of the important properties that we need for that variance. The big thing that it will do, so when it doesn't remove the meaningful pieces of the variance that we want. Michael, I'll let someone else answer your question about cat codes. So we actually want to normalize the interest rate as well. And we want to normalize the interest rate so that because we know we have different means and different variables there. A big part of why we're normalizing is because it will make it easier for us in the next steps to interpret our coefficients. One of the really hard parts about logistic regression is understanding what the coefficients in the model mean. Standardizing will make it easier for us to interpret those coefficients. It will make it easier for you to explain to a stakeholder, what does this coefficient mean and why is it important? And I'm going to repeat that again. because I think that's important. It's important to standardize variables in logistic regression because it makes them easier to interpret. So yeah, Viviana, you're right. We're not changing the, I think that is more difficult to explain. We'll get into I'm going to ask you to take a leap of faith. Como se dice? Leap of faith. Little jump. Saute? I don't know what the word is for that. It doesn't make sense now. It'll make salto de fe. Okay, there you go. It sounds a little bit counterintuitive. I promise you that doing this standardizing will help. It does, so it won't affect the model. This is the most important thing. It won't have a meaningful effect in this kind of model. In a more complicated model, it might, but in this particular kind of model, it won't. And again, the reason why we're doing this is because it will help us to better interpret the coefficients that are being used in our model. It's very common to do this as well with linear regression. A lot of times when we do these analysis, we will normalize variables for a linear regression too. But it's critical to do this so that we understand the motivation and understand how to interpret the model that we're producing. I see one person typing. Yeah. So mostly just make sure that everything is operating. We're talking about changes. We're talking about unit changes of difference, right? So when we standardize, it's easier to say, here is how much of a difference that when we go up by 1 unit, and it makes it easier for us to talk about to compare the coefficients in our model to each other and talk about which things are having bigger effects. This becomes important because we can't do the same kind of analysis that we did in the past with squaring coefficients to get R-squared values. Okay. Here, we're going to display our results here so you can see what these results look like. We're going to look at our value counts down here. And again, this is showing us that the 1 is the probability that the loan is not going to be paid off. And 0 is the signifier for a loan being charged out. That's the thing we want to avoid. So we've structured this model so that most of our results are a 1, not a 0. Can somebody answer Catherine's question so that I can focus on this next bit? Notice that for most of these, that's exactly what we're doing here. Again, we've converted these into cat codes so that we're basically doing an encoding on those. All right. So the first thing we're going to do is a simple model. We're going to treat our loan, and this should be a really familiar piece to you. This is a formula to calculate the ordinary least squares regression. So we're looking at loan status. And what are we predicting? What are we using as our predictors? Well, we're saying verification status matters. We're getting the annual income. We're looking at loan amount. We're looking at our interest rate. And we're looking at our term. Donna, in this context, standardization and normalization are almost the same. Are almost the same thing. They are sometimes used interchangeably, and sometimes they mean slightly different things. But in this particular case, they are the same thing. Okay. How can we interpret this? So Daniel, we're building a simple model first. We're only looking at the variables that we've converted into these categories. So we're looking at loan status, verification status, interest rate, loan amount, term, and grade. We could use one on hot encoding, and we will do that later, but in this particular case, we just did it with these categorical codes. I'm mostly doing this to set this up in a little bit simpler of a way so you can show, so I can show you the thing I'm concerned about. But it'll be clear in a minute. Okay, so we have variables that we know should have that we know are related to that we know are related to these bits. Okay, so let's look at our two pieces of information that are probably really interesting to us. That R2 is really close to 0, isn't it? We're not explaining very much variance in the model. But that might be okay. That might be okay. But so let's go look at our verification status down here. How would I interpret that coefficient? Does verification status have a meaningful relationship to loan charge-offs? We'll talk about category imbalance and the response variable tomorrow when we talk about cross-validation. But for right now, we're not gonna touch that particular hot potato, right? So based on this linear regression, we have two big problems. This coefficient is having a really small effect. All the coefficients have a very small effect, and the R squared is overall very tiny. Carlos, right? It's a little bit worrying. Okay. So I'm going to skip this little bit about what can we conclude from these results. We've basically gone over that already. Yes, you should all be shaking. You should all be very, very worried. Linear regression has failed you. So interest rate might already be capturing the risk. Sebastian, that's a very good intuition. We notice that all the other variables do have statistically significant effects. But these coefficients are all quite small, aren't they? Well, Juan, we're going to look at that in a minute. Felipe, you are cued on to a really, really critical point here, which is that we're trying to measure a I don't know, a foxhole with a ruler. I don't know if that's an expression. It sounds funny though. We're trying to capture something that doesn't quite fit into what we're thinking about. All right. So even when we add more information here, we're still not producing a lot of the information that we want. That is exactly right. So, Matteo, let's surprise us with the logistic regression. So I want to talk about that. And Alejandro will talk about that image in a minute. I think that's actually really, really good. And that gets at a very important idea that's critical to what we're doing here. But Matteo, why are the p-values small if the line doesn't fit? Why would the p-values be small here? Is there capturing something important about what's going on? Is there enough information in there for it to capture that? Yes. What's the other big thing that really matters? How big is this data set? Santiago, yes. The model that we're using, the logistic regression uses a likelihood model, not a residual model, but that's not actually what I'm trying to get at here. Sure. So with a sample of, I mean, you can do the back of the envelope calculation, but how big of a difference can a data set with a sample of 38,000 detect? How small of a mean difference do you think it could detect between two things? We saw it before in the t-test. An income difference that is as small as 6,000 can be statistically significant in this data set because we have a very large data set. Well, not very large, but we have a large data set. We're working with a very large data set, so even small differences can be statistically significant. And this is key when we think about power, when we think about not power laws, but we think about statistical power. We have a really, really large data set. So based on our statistical power, our type 2 error, we can detect very, very small differences and they can come off as statistically significant. Part of your job as a data scientist is not just to say, look, here's a statistically significant difference. Part of your job as a data scientist is to look at those differences and say, which of these are important, which of these are not. And again, that's what this regression model is picking up. There are enough differences, and there are, like, the linear regression is strong enough to pick up on those those differences, those tiny differences, but it's not good enough to capture the broader differences in the model. Okay. So let's actually go, let's just go grab this picture. Well, actually, we're gonna do this first. So I want to take a look at this model. And again, we can just download this. Open, there you go. So let's talk about what's going on here. Alejandro, thank you so much for saving me the time of having to go pull this up myself. Machine Learning India. This is from StatQuest, man. All right, so here's what's happening. And so let's think about what's happening from what we know about a linear regression. How does a linear regression work? How does it evaluate the goodness of a fit? And how does it figure out where that R squared is? What are we trying to do when we're fitting a model with linear regression? I have no idea why you're getting slightly different numbers. Exactly, Matteo. We're looking for the low sum of squared residuals. So what's happening here? Well, again, when we're drawing this linear regression, it's sensitive enough to be able to say, okay, for this particular variable, it can get at some of these little bits in here and say, oh yeah, that's a little bit, I can capture these things. I can capture enough of the difference here to be able to get a statistically significant beta. But how would I draw? Ooh, can I draw something on this? I can draw. This is going to be terrible, folks. Ooh, let's get a different color. Black like my soul. There's a residual here. There's a residual here. There's a residual here. And again, I'm trying to layer these on so you can see them, but they're not actually going to be diagonal like this. These residuals here are all getting bigger and bigger and bigger. The size of these growing residuals is impacting the overall fit and impacting the R squared. Yes, Maria, we're going to talk about sigmoid functions in just a second. So again, think about what we're doing with this line here. We're trying to draw this line. We're trying to draw a line through these points, and there's no way to tilt this line that's going to reduce those residuals. So there's no way for the regression to minimize that function. So there's no way it can say, hey, I found a line that's capturing a lot of the variance. This is sort of this is the problem that we're running into. And again, you all have done a great job of identifying what the key point here is, which is, go away. Which is that we've got to think about a different way to capture this. And in this particular case, we're going to do, yes, Juan, that's perfect. So we've got to do, we're trying to actually fix we're trying to fix 2 or 3 different problems here. One problem is that a residual model, by just trying to identify residuals, by trying to do our fit here, isn't going to work quite the same way. So we don't have a linear model here to capture these differences in residuals, so we need to use a different estimator. We need to use something else to minimize or maximize for fitting our line. Maria, logistic regression is a great option for a categorical variable. We'll talk about a few, and logistic regression is an excellent tool for classification problems. There are lots of other tools that work well. We'll talk about the advantages and disadvantages of each. Regardless of whether you use logistic regression as the tool or not, you need to know how logistic regression works because it will help you establish a baseline for how well your other models work. Logistic regression is really powerful because it's relatively simple compared to a lot of other classification tools. And so it has a lot of value as if you can't do better than this logistic regression with these variables, then you need to reevaluate your model. And sometimes you want a logistic regression. Sometimes that is the thing that you need to produce the answer that you want. Andres, there are several kinds of logistic regression. There's binomial regression, multinomial regression, and ordinal logistic regression. In this particular case tonight, we are talking about binomial regression, which is just 2 categories. Okay, so we have this problem to fix with this line with the residuals, so we need to use a different tool to capture that. The other thing that is more fundamental, and I want to say that if you don't use OSL for the binary dependent variable, the coefficients are now, well, the coefficients, what's the right way to say it? The coefficients from an OLS model are still interpretable, like you can use them to say something, they just don't tell you very much. And again, if the coefficient is small and near 0, and the R squared is very close to 0, then yes, like you can definitely probabilistic regressions. Oh, well, and that's a pretty in the weeds question. So there's logit and probit models. They use different they use different probability density functions. That is not what we're worried about. Yes, that is very good, Genesis. This is excellent. Well, you can use linear. I would actually push back on that little figure because you can solve a logistic regression can be used to solve a classification problem, but technically it's a regression tool, not a classification tool. But we'll get into that. Juan, to answer your question about logistic and probabilistic regressions, they assume different models for the cumulative functions. In terms of the work, and they'll produce slightly different coefficients based on those assumptions. The only for the scope of this course, you don't need to worry about the difference between a logit and a probit model. If you are going deeper into these things and trying to build more complex models, or trying to build models that were capturing different kinds of more complicated models of variance, then you would want to start thinking about using a probit model. But for the purposes of our course, a logit and a probit are going to be doing the exact same thing. They just have a slightly different density function underlying them. Maria, that's amazing. I love it. So we also have to write a function that can map the core of our data. So I don't want to get super duper in the weeds about what a maximum likelihood function is, because that is what we're using, and that's what's replacing the residual. But a reasonable way to think about it is an ordinary least squares model is saying, I want to make the differences between this line and these points as small as I can. And a maximum likelihood function is saying, I want to draw this line so that it gets as close to hitting as many of these bops as possible. And those sound like very similar ideas, but they require a little bit different math. And the differences in those pieces of math can and do fill entire textbooks. But it's the core idea of a maximum likelihood function that we are trying to predict likelihood, and which basically means how well can we draw our line to pass through or on top of as many of these dots as we possibly can. All right. Everything, Andres. You can literally, I mean, this is the other nice thing about a linear regression. You can literally throw all kinds of things inside of it. It also is a very efficient algorithm. So you can run it on data sets that literally have millions of observations of data, and it will run in a very short period of time. And random forest classifiers and neural networks just don't do that. Okay, Mateo, is it possible to transform data to put values y equals 0 to the left and values y equal 1 to the right to fit better on logistic regression? I don't quite know how to answer that question. The short answer is yes. That's exactly what we're trying to do, but it's a little bit more complicated than that. Okay, we've been staring at this picture for too long. So David, this is a really good question. And I think actually that someone in the chat posted a really good explanation. Genesis is the model from Genesis. You don't want to use the R2 value because actually, and we'll get into this in a little bit, the logistic regression doesn't produce an R2 value or an R squared value in the same way that a linear regression does. Okay. Yeah, I think, David, your question is, do ordinal logistic regressions, are they the same as ordered logistic regressions? That looks like just a slight difference in terminology. I think that's probably fine. I think those would be the same thing. I think that's just a slightly different naming convention, but I'd have to go double check on that. All right. So somebody had the observation, and I want to get into this, is that what are we trying to model here? And I wish I could identify who had said it. What are we trying to model here? Ultimately, are we trying to predict zeros and ones in our model? We are not. What we're trying to predict here. Oh, perfect. Thank you so much. Thank you so much, Oscar. What we're trying to predict here is a probability, not a p-value, but a probability, a number between 0 and 1. Now, one of the problems that we have is that, well, we know we can have values between 0 and 1. And we want to draw that S-curve so that it goes through as many of these points as possible. So what we have to do, okay, David's answering all these questions, fantastic, so I can talk about this other stuff. So what we have to do is do a little bit of transformation work. So we want to predict a probability, and we want to we also, for a regression, have a number that can go all the way from negative infinity to infinity. So we want to create a mapping. We want to use a number that is going to keep the same information. That's an algebraic transformation of a probability. Excuse me. An algebraic transformation of a probability that can go from negative infinity to infinity. So the first thing we're going to do is take our odds. I believe though an odds are, apuestas. Yes, I have it on my little note card. TAs gave me a note card of helpful Spanish words. So the first thing we're going to do is convert our probability value, the value we're trying to predict, and turn that into an apuesta, an odds ratio. So what are the values that an odds ratio can run from? How small can an odds ratio get? How many horse bettors do we have in here? How low can your odds go? There you go, Sebastian, perfect, 0. No, the inverse tangent is not going to help us here, Santiago. But not a bad guess. And how high can the odds go? Nope. 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 How high can odds go? Infinity. All right. Okay, I've had it. We have to answer this question. NPI, is that Spanish for infinity? How do you say infinity in Spanish? ¿Cómo se dice infinity? Infinito. There you go. Odds go to infinito. Apuestas vamos infinito. Is that right? That sounded like very good. I don't think that's good Spanish. Okay. I'm going to do something terrible and you're all going to hate me for forever, but I'm going to use an Excel file to teach you some data science. That's fair. Oh my Slack just died. That's not good. All right. Okay, it's back. I know. We do all this fancy work and go learn Python and SQL, no. And now I'm like, whatever, just show it to you in an Excel file. Okay. Odds, apuestas. Here's a value really close to 0. And we get to 0. We teach you Spanish, you teach us. Yeah. All right, so at 50.5, we get an odds of 1. At 90, we get odds of 9. Whoever said that the upper bound of odds was 1, you are missing a number. If we go to 0.99, the odds are 999. If we go to 0.999999, it's going to get real mad at me. Yeah, it doesn't like that at all. And see, it won't even let me do that. Excel gotta love Excel for a rounding error. I want to point out this is why data scientists hate Excel, because I had to do this kind of crap all the time. It assumes formatting is real. And we all know formatting is just a joke. There you go. See, look at all those decimal places. This is ridiculous. We're not going to do any fancy Excel tonight, Daniel. Don't worry. All right. So as we get closer and closer to the probability being 1, we get a higher and higher. We get a higher and higher. You don't do well. We're doing Excel now. You got this far, and all you can do is in Excel. Okay. So the thing I'm trying to motivate here. Yeah. So we have our P value, and odds will get us from 0 to infinity. Correct. Odds is different from probability. Odds but it has a strict mathematical relationship. Apuestas. Am I saying it wrong? Probabilito no es apuestas. Is that right? I really think that's terrible Spanish. Perfect, Daniel. Yes, odds is more like chance. Ah, okay. Yes, probabilidad is different. Very good. Yes, exactly, Sebastian. Okay. Maybe. I don't know. TA has told me to use apuestas, so I'm telling you apuestas. This is my very broken Spanish trying to explain math. All right. Apuesta. Okay, perfect. Yes. Well, I mean, it is. It's a thing you use in gambling and in casinos. They use odds. Yes. Apuestas are your bets. That's perfect. Yes. Okay. Yeah. Apuesta is exactly what we want to use here, though. Apuestas is a bet. This is a bet. This is saying, here's the ratio of it happening to it not happening. Yes, if your odds are infinity, then your probability is 100. Perfect. Odds are useful because they move us into this 0 to 100. Yes, I said gambling just to get your attention, Daniel. So I'm doing this second transformation, and I'm doing this transformation to go to log odds. Now, why would I do that? That sounds very confusing. Oh, all right. Thank you, Catalina. I'm converting this into log odds because this gets me to now I have a value, and we're expressing it with that sigmoid function that will get me to a range of numbers that go from 0 to infinity. Notice if that, God, yeah, the disadvantage. All right. But again, I wanted to show this to you so you could see, okay, this is the relationship between the probability and the odds ratio. So we have a value that can go from 0, negative infinity to infinity, and maps perfectly onto our definition of probability. So we can get back to probabilities. Because ultimately, what we're trying to predict is a probability. Okay. So we've now gone through all of this. Okay. So I've kind of shown this to you. Are there other questions, before we start getting into some of the code and looking at some of these results, are there questions I can answer for you about how this works? Do people feel like they're getting it? Can we get a poll and answer? Do people feel like they have an understanding of logistic regression or of what we're trying to do here? Why we're using a sigmoid, what probability, and what the odds are? Ooh, Anna's typing. Okay, I'm going to keep going. So we're going to look at now some code to run a logistic regression. I don't want you to spend a whole lot of time worried about the code. You'll be able to review that more carefully after this. Oh, perfect. Yes. Okay. Thank you so much, Anna. We're going to build a model. We've got our verification status and our loan status. We've got category codes. We're going to manually code an intercept in here. Okay, we're doing, we could be doing better. There are a lot of crazy angry parrots. I don't like that sign. It looks like we still have some questions about logistic regression. So we will interpret more than that, but we'll start with the sign. The problem is with a logistic regression, when we're looking at the output from this model, this coefficient is a log odds ratio. So this is Miller. This is a unique thing about logistic regression inside of Python. You have to explicitly define the coefficient to be 1. Occasionally, you have to build a model. Oh, Genesis, thank you so much. I wish I could read that. Okay, perfect. In logistic regression, you can build a model that doesn't have an intercept. In any kind of model that you'd be building for any kind of most data science work, that's not the case, but they built it this way anyways. So you need to expressly define your coefficient here, and you need to remember to do it. Yes, you always need to add the intercept column, David. There are situations where you don't want to use it, but the situations where you wouldn't want it in there are not relevant to almost any use case that you would have. So we're looking at intercept and verification status, and they're predicting our loan status. Okay, we're gonna go for like another 4 minutes, and then we're gonna move on to how to evaluate this. So the thing I want to point out here is we've used MLE, maximum likelihood, which again, we're not getting too deep into, but is core and is very distinct from what we do with OLS regression. We have our log likelihood value over here, which is critical to how we're analyzing the data. Oh, perfect. Thank you. So this coefficient down here, the basic interpretation is as that number goes down, if it's a negative value, it's reducing the risk. If it goes up, it's increasing the risk with whatever is defined as 0 and 1. So in this particular case, verification status is reducing the risk, and it has a statistically significant p-value. We can identify the confidence interval here. They're imagining it is not a binomial trial, even though it is, Sebastian. It's not. I don't want to get into it. It's an and, not an or. Or rather, it's a given this has already happened and we've assumed this has happened, they're implying that the trials are not independent, even though technically when we think about coin flips, they usually are. Why is the coefficient negative if it's a ratio of positive numbers? Okay, the reason we're thinking about this is you can have a negative coefficient because the negative coefficient is dropping down that odds ratio. It's reducing it. We'll talk about pseudo R squared in a minute. So Maria, there's two ways to think about interpreting. The simple interpretation is if the coefficient is negative, it's reducing the risk. If the reducing the odds. If it's positive, it's increasing the odds. And so what we can see here is that verification status is reducing the odds here. The intercept is not telling you a whole lot of information here. Technically, it's tied to the base rate, but that's not always the way it's going to be useful. So we've set the intercept to be 1 here as kind of a dummy variable, as we don't really know what it is, so we're just going to leave it in here. We need to have it in here because of the way that this particular stats model incorporates the idea of an intercept into a logistic regression. So that's a really good point. So that's why in this particular model that we're looking at, so in this particular situation, we have a pretty clear ordering, and we're able to, when we structured our categorical order based on that. In general, what you'd want to do if you have a lot of categorical variables is encode them as dummy variables. And we'll talk a little bit about that in our next step. Okay. So the one thing I want to point out here is someone asked about the pseudo R squared. Pseudo R squared is a measure of ratios of log likelihoods. So it is the core metric that's used to evaluate this and deriving it from and comparing it to a base model. The problem with the pseudo R squared is that it's not very useful for comparing two different models, but it is sometimes useful for comparing the same model that's looking at the same variable on the same data set. So if we have different data, we can't use it to apply this. And if we have a different outcome variable or different other kinds of outcome variables, the pseudo R squared doesn't tell us very much because it's a relative, it's sort of the basic way I think about it is it's kind of a relative ratio. It's saying, here's how good this thing, here's like what we think is like the worst case scenario for this data. And the R squared is telling us how much better we can get in terms of predicting. It's useful in some contexts, but not in others. The big thing though is that you can't use it to compare models to each other. So we've got to use an alternative method to do that. And that's what the next component of our analysis is going to be. So I like to end on a relatively, we're going to skip this component right now about the geometric interpretation of logistic regression. The only big thing I want to take away here is that this visualization of the data. Oh, there we go. The big thing to think about here is that linear logistic regression, even though we're drawing a sigmoid curve, has, when you use it for a classifier, it does create a linear boundary. Other variables that we look at, or other models we look at, will not create a linear boundary for good reasons and for bad, and we'll talk about what that means. All right. Don't really need to get into that. Okay. So last big thing here. A regression model just gives you, spits out probabilities. It doesn't tell you how to evaluate whether something actually goes in a 0 or 1. And that creates a problem. We can't really use precision and recall the way we would like. And a pseudo R squared, because it's a relative measure based on a likelihood model, it doesn't give us enough information the way that an R squared does to really compare the model. So an R squared is useful in some contexts, but it's not useful to compare this model to say another model with different sets of data in it, which is a problem. So we need to motivate a different way to get there, and we're going to look at something called the ROC curve, or the receiving operator curve, and we're going to do that after the break. But I want to give you all a few minutes to let this digest. Let's take a short 5-minute break for arepas and oblas. And I think that's where we are. All right, everyone. So, congratulations. We made it through a very difficult part of this case. We have one more piece left to get through, and we're in the final countdown. I think I think that's the right word for it. Let me share my screen. All right. We're in our final rounds here. And the big thing I want you to think about, is that in this home stretch, we really want to focus for this last little bit. We're going to talk about one of the most important things, which is how do we go about selecting our cutoff values? How do we turn our logistic regression, our model of probability, into something that can answer the core questions we want to answer? And to do that, I'm going to give you a very tricky tool. It's full of tricks. It's very de Despacito, no, de Eblacito, demis trickiatio, or I can't remember the word. Anyways, yeah, I think so. Very, no, not Despacito. Okay. Triniquela? I don't remember the word now. This is not good. I got to write this down. Okay, I'm gonna get my, oh, no, not complicado. Mañoso. I have it on my card now. See, it's backwards. That's fine though. Mañoso. We have to be tricky. We have to think tricky to get this last part. But this tricky part is the part that will set you apart. Good Spanish. Okay. So we've talked before about the idea of a true positive rate and a true negative rate. We've talked, and when we talked about this before, we are full of slang. Mañoso, why is that? Is that slang? I have so much vocab now. Socromático? I've got so much work to do. This is you are keeping me very busy, Columbia fellows. All right. We're talking about the true positive rate and the true negative rate. We've talked before about true positives and false positives in the context of our p-values. We're trying to reduce our worries about, we're trying to eliminate false positives and false negatives. This is the bet. I do not believe you, Sebastian. I've not, nope. Daniel, that's a non-starter. Nope, can't deal with that. Okay. We want to be able to identify and think about the logic of what we're trying to do here. Malicia in, I don't know what that is. A true positive rate. We want to be able to pick out all of our true positives here, all the things that we know that are going to be a problem. We also want to identify our true negative rate. We don't want to overpredict. In our context, TPR measures the people who've paid off their debt that are correctly identified, and true negative captures the proportion of defaulters. Now, this is something that people will argue about, that data scientists will argue all day about which one you should treat as the 0 and the 1 and this kind of a thing. It doesn't matter as long as you're consistent and as long as you understand the direction that these things are going. So keep in mind here, our true positive is capturing people who've paid off their debt, and true negative is the proportion of defaulters. We absolutely need to keep that very straight in our minds. So think about this too. There's got to be a constant trade-off between true positives and true negatives. We can't build a perfect model, but we can either predict all of the true positives or all the true negatives, but in general, getting better at predicting one means getting worse at predicting the other. Well, Jessica, it's very good you asked that because we're going to exactly talk about it. Carolina, yes, exactly. True negatives are the most important in this case. And so if we were building a model of how to do this and building a model to identify that, and identify where we want our cutoff point, identifying the trade-off between the true positive and the true negative would be essential for what we're doing. All right. I'm actually going to skip this exercise and leave it to you as the reader. But the only thing I really want you to pay attention to here is that if we say everything above 0.8 is true and everything below is not, we get this for our true positive rate and this for our true negative rate, and they flip between 8 and 9. So one of the reasons this is hard is because as Carolina points out, a true positive and a true negative have different expected values. They matter more to companies than others. True positives in this case are important, but there are a lot of them. True negatives cost the company a lot of money. So you would need to build an expected value model that would tell you about how you would weight the importance of a true positive and a true negative. But this is, thinking about it this way is an algebraic way to think about it and a coding way to think about it. I want to show you a visualization tool as well that will help you understand the core trade-off between true positive and true negative. And that visualization is the receiver operating characteristic curve. No one ever calls it that. They call it the ROC curve. The receiving, there are lots of good reasons. There are not a lot of good reasons why it's called that. It's a very technical term because technically it's identifying the way that it's defining the way that sort of conditions are valued and what true positives and true negatives are called and thought about from a mathematical model. But what I want to show you here is this model, and I want to talk through several important points on this model. It's actually, yeah, it's an ROC curve. It's not, yeah, it's related to a QQ plot. That's actually a good, what's the word I'm looking for? That is a good starting point to think about. So let's talk about what's happening in these different models. Down here. So at its core, we have a false positive rate. We have a true positive rate. We can go from 0 to 1 and 0 to 1. And we're trying to plot how our model does in terms of where it's predicting. Down here, we have a model where the false positive rate is 0 and the true positive rate is 0. This model is predicting that everything is false. It's saying everything is false. All the values are 1. If it has oh, Catherine. You're going to build more than one of these. You're going to build so many of those. These you will become very sick of ROC curves. They will make you cry. I am sure that's exactly what you wanted to hear. Down here, the false positive rate is 0 because we're saying everything is false. Everything is false. If we say everything is false, we can't repeat. If we're saying God, I got to get my brain wrapped around this. If the false positive rate is 0, we've identified everything that can possibly be false as false. It also means our true positive rate is 0. Up here, we have the opposite problem. Everything is a false positive, and our true positive rate and our false positive rate is none. This is another naive model. This is another model that's saying we're just going to put everything in the false bin. Excuse me, we're going to put everything in the true bin. Yes, perfect. Thank you, David, for answering that question. Now, what's happening right along here is your random guess model. Yeah, ROC curves are everywhere. They are a universal tool. And again, they're universal because they can apply to lots of different models, and they are useful for looking at lots of different ways that you can think about true positives and false positives. Right up here at the very top, our true positive rate is 1, and our false positive rate is 0. What happens if we get a model that's right up here? If the false positive rate is 0 and the true positive rate is 1, what's this model doing? Is this model really bad or really good? Exactly, David, exactly, Juan. It is a perfect model. Exactly. We want our model to get as close to this spot as possible. Now, here is the random guess line. This is where we're wrong half the time, right half the time. What happens if our model is worse than a random guess? What do you think that would, what would we think about a model that's like that? Terrible, terrible model. Absolutely terrible model. Right, it's very good, Carol. Oh no, it's not. Yes, Daniel, it's not even a squiggle. It is a very bad. Yes, it is such a bad model. You have to take it out. You have to take it outdoors and spank it because it's been a very bad child. It's worse. It's a broken coin. Well, even the curve exactly, Danilo. It would be the curve would be convex. Y label should be 1 TPR. Yes, that's correct, one. So when we're looking at a model, we generally know that a model won't end up anywhere in this. I don't want to do that. We generally know that a model won't end up anywhere in here. This is no-go, the no-go zone. Well, you don't want to necessarily invert it. We know this spot up here is the perfect model, and these points are two naive models. So what we're really thinking about is, okay, what can we tell about the model, the ROC curve for the model in exercise 6? It's above the random guess line, right? So it's doing it better than a random guess. Does that make sense visually? Oh, perfect. Thank you for posting that in the chat, Oliver. Oscar, good Lord. Okay. Fantastic. Okay. If you inverted it like that, that would be a problem, but that's not what we're doing, so that's okay. So what we can tell right now, just by looking at this model, is our ROC model, is our current model perfect? No, definitely not. But you can visualize it, right? So I can say it's not a perfect model. It's better than a random guess, somewhere in the middle. It's barely better than a guess. How would I quantify how much better than a guess it is? How would I do that? How do you think I would do that? John, you're spoiling all my fun. I wanted to make everybody guess. Mauricio, you do have to set a threshold, and that's what this is helping you to do. Diego, yes, exactly. And Juan, very good. We have to calculate the area under the curve, and we can look at different models and compare basically how much space is in this gap between the random guess and our model and how close it gets to up here. All right, I'm going to get rid of this now. Ooh, I need to get rid of my annotations. Clear. Oh, go away. Oh, there we go. They're all drawings. There we go. Thank you. All right. So we're not going to, I want to keep this short. So again, you need to review this coding, these pieces of coding. Okay, so why are we not using a confusion matrix? What's the problem with the confusion matrix right now? Is logistic regression a classifier? No, Manuel, you are on point. Juan, exactly. Yes, that is. We have more information here than what we would get from a confusion matrix because we are able to quantify this in a more subtle, in a more direct way. You're a confusion matrix. I am a matrix. It is made of confusion. The area under the curve here is giving us more information than a confusion matrix is because we're able to more directly compare the two differences. Now, the nice thing about a confusion matrix is that we can tune it to precision, recall, or an F1 score, depending on what we want. But we have more information here because, yeah, we also need a threshold for the probability in order to classify. That's another excellent piece of information here, Alejandro. So there's, again, so there's kind of two pieces here. Well, Alexandra, tied to what Alejandro said, and going back to what, oh gosh, I don't remember who said it. We don't know what that proportion should be. We don't know what the classifier value should be. We don't know what we don't know what that threshold cutoff number should be. The ROC will help us figure that out. But this is a way to more directly evaluate and say, how well is this model doing in building? And how can we more effectively compare different logistic regression models to each other? And that is what we're getting at with this with the ROC curve and the AUC. Excuse me. So we built another model up here, the logit rest model, which just has the intercept and verification status. And what can you tell about these two models? Is the green model better or is the orange model better? No, the green model, they're both logistic regression models, Sharon. The ROC curve, the orange model is the model from exercise 6. The logit res model that we're building up here is a simpler model. Green has the greater area. Exactly. So this gives us a way to both visually and quantitatively assess the differences between two models. Daniela, that's an amazing image. That's perfect. Yes, that's exactly right. That's exactly how, yes, Daniela, that's exactly how to think about that. Juan, that's the exact idea. You're going to, in the same way that you would build, this is where we get back to the theory, get back to the process that's like a linear regression. We compare ROCs and AUs, we compare ROC curves and AUC curves, and it provides us with a much more meaningful way to compare different models and compare them in a way that is not tied to those log likelihood values. So they're more generalizable to each other. Yes, Alexandra, the further away from the random guess curve, the better. So we're not quite, Jan, we're not quite concerned about the optimal point yet. Again, because remember, the optimal point depends on the expected value and depends on depends on how we identify the utility of different misclassifications. Modesta, are you tired or have you gone to sleep? Okay, so all we need to do now is calculate. Juan, I'm a little worried about you, Juan. He passed out. That's fair. I know this part is scary. This part is hard. So I do want you to review this. I will put together some links and some stuff to help talk about this as well, so you can read and watch some videos. But again, I want to make clear this is one of the most complicated things we're talking about. It's of the night. It's also very central to what we're doing, and we couldn't get here until we had gone through these other information. Esta es la parte más enredada. I don't know what that means. I guess I'm gonna have to go look that up. Okay, I've got to write this down. Tangled. Well, okay, enredada. It is difficult. It's supposed to be difficult. This is like, we're trying to create something that's we're trying to do something that's really hard to do. So it's okay that it's hard. It's okay if this blows your mind the first time we've done this. If that will be me. That will be me in like 5 minutes. Okay, perfect. Entrada. So the core idea here that we're trying to get to is, and now we're getting back into the part where we can think about what we did with regressions before. We can calculate the area under the curve. Look, we have a fancy, cute little function that literally does it for us. It compares these models and we'll calculate these two curves. So we can literally say, and these are values that go from basically 0 to 1, 50% is the random guess curve. And this gives us the core piece of information that we want. Okay. What was as I recall, we were trying to get around to evaluating something important. We were trying to get an answer. Oh, all right. So Harold, this is the information that we are trying to calculate about the area under the curve. And the big thing about the area under the curve here is, again, this is the visual explanation of it. Cell 43 right here is how to calculate it. And you can see that we can get a quantifiable difference between these values. This quantifiable difference gives you the information that you need to be able to evaluate models. So we can now explicitly say, if we add this variable to the model, we can be certain it's better than that than that model. We can't really do that in the way that we would want to with a pseudo R square. It's not robust to that. but this is. So what we can do now is take and look at contingency tables and calculate the additional value that adding the verification status has after including all of these other models. So once we've accounted for the variables we know are related and are confounds that are screwing up how we account for verification status, once we include those variables and variables like income and loan amount and term, we can see if we're adding additional value by comparing a model with and without verification status. We are now, 0.5 is the baseline of the random guess. Yes, exactly. Thank you, Carol. ROC and AUC let you have give you a robust way to compare models by adding and removing variables. This is the thing we need to do to answer the business question. This is the hard part about data science. People ask you something they think is a simple question, and it's actually very hard to do. Somebody asked you, does verification status matter? Does it really add value to do it? Do we get more information by doing it? That's not a simple, it sounds simple. It sounds very simple. You can see almost 3 hours later of me jabbering that it's not. And this is at the heart of what we're doing for data science. We have to find a way to answer a simple question, what appears to be a simple question, in a robust manner. So note here that we're going to build a model. We're going to get dummy variables down here for home ownership, purpose, and grade. We're going to drop our first variables here because we don't have an ordinal relationship between these models. We're going to standardize our loan amount, our interest rate, and our annual income. We're going to put our verification status in as categorical codes because we know a rough ordering of them, and that's the bit we care about. We're going to encode our employment length again as categorical codes because we know generally what the rough order should be. And we're going to again code our intercept because that's how we do this. And we're going to run our logit model. Now I can look at this. I have coefficients here that tell me about these different pieces. Verification status is down here at the bottom. Is verification status statistically significant? Most definitely is not. If we include it in the model, can we create two models, one with it and one without it, and look at the AUCs and the ROCs to see if they are Yes, Jaime, that's an excellent point. We can have confounds, and that's exactly what we've been investigating tonight. How verification status is confounded or related to other variables, and we've seen that with the Simpson's paradox. All right. I want to see if there's one more visual. Okay. We are running out of time, and I want to do a hard stop at, we need to do a hard stop. I'm not going to hold you for longer than that is not a thing you need. Okay. I apologize. Okay. So we're going to skip over this next little bit. I do want to go, we can get into that and we can go over that a little bit more tomorrow. But the core thing I want to highlight to you here is let's look at our two models. And again, thinking about the ROC curve, the rest of that stuff is just the rest of the stuff we skipped over here is a little bit of arithmetic. What do we see here? We built a model with verification status and without verification status. Has the area under the curve changed? the area under the curve has not changed. And so what we can say with confidence now is that verification, yeah, thank you, Sebastian. We can say with confidence that including verification status in our model, it's not statistically significant, and it has no practical implication for the model once we include our other variables. And again, tied to what Jaime said, we do observe a relationship at a simple level. When we just look at verification status and loan status, we have observed that, but we can explain why it occurs. And it's largely driven by the fact that different people with different there's confounds. There are variables that are related to verification status that explain away the difference. All right. So trust people at first, LOL. Or so the reason the verification status doesn't matter is because we have excellent information about other things. And so there's no new information contained in the verification status. Christian. The core idea here is that we want to identify if this verification process, which takes time and is expensive, does it actually improve what we can do, or can we drop that annoying and expensive process? And the answer we're getting from this is, yes, we really can. So I want to walk through. So Alexandra, that is an excellent question. The results could change if we did one hot encoding, Diego, but based on the pattern of other results that we've seen, we have very strong reason to believe that it would not. Well, actually, one hot encoding wouldn't matter. We could create dummies for each category, but it's unlikely based on what we've seen from these other results that we would see any difference. I'm also not going to do that because I don't want to try to live code on something that's complicated. So I want to walk through the core. Perfect. I want to walk through the core ideas here of what we did tonight, because logistic regression is hard and there are multiple steps to what we did. So we were trying to ultimately answer a question about whether or not a variable should be used, whether or not verification status impacted loan repayment. To do that, we really had to do 4 different things. The first thing we had to do, and again, this is the most important part, this is the part that was hard, we had to perform EDA on our binary outcome using our cross tables so that we better understood the core of what was existing in the data. We had to be able to identify and root out our Simpson's paradox. This is a very common example of where a Simpson's paradox might emerge, and you have to be prepared for them. They emerge all the time. Second, we had to perform statistical tests to generate hypotheses. So I skipped over the exact scientific language here because I was trying to focus on a slightly different point, but we kept increasing the rigor. First, we looked at our cross tables. Then we did a couple of t-tests. Then we did a chi-squared test. Then we started using our logistic regression. And again, as we are doing these steps, we are increasing the rigor of our analysis. But they are the same thing. They are trying to tell us the same story. We're trying to answer the same question. They are just steps in a process. And we are increasing the rigor. We're asking ourselves stricter and stricter tests of what's happening. We codified and tested our hypotheses with larger models using logistic regressions. And again, that's tied into what we did. We took the leap. We took the leap into larger models and logistic regressions and talked about why, in this case, we needed logistic regressions and not linear regression to answer our questions. The last part was, okay, once we built these logistic regressions, how do we compare them? And how do we compare models with and without verification status in them? These models are just codifications. They are just clarifying and making more rigorous, creating more rules around the core analysis that we did. And we assess that classifier performance by looking at the receiving operator curve, the ROC curve, and evaluating the area under the curve. So basically testing how good our model was at identifying true positives and its true positive rate and its true negative, true and false positive rates, excuse me. So logistic regression is really critical in your life as a data scientist because it is a bridge. It's where we start with linear regression and we use the ideas of linear regression to start getting into questions about classification. And that was really important for things that you'll be learning down the road related to neural networks, related to classifiers and decision trees. They are core to the work that you'll be doing down the line. And I think that's actually pretty much all the stuff I want to say. So the only thing I want to, the thing I want to identify here is that logistic regressions are simple, but they're powerful and they're important. They're an important step they're an important piece of our data science toolkit. All right, Monica, it is that time, and I think it's time for you to kick it up.
Okay, thank you very, very much, Scott. And fellows, we know this is a very difficult and dense lecture, so that's why we invite you to review the recording once it's available. So thank you very much, and now it's time for a rest. So great to have you here. Thank you very much again, Scott, and see you tomorrow.
Oh yeah, I'll be back tomorrow night, friends. See you then.
Take care, bye.